Hi everyone. So I found another example and I decided to do an example that I haven't used in last year or previous years. And that way you'll get the real live thing. And this is one that's a little bit harder and haven't done one like this, at least not in the last several years. And I wanted to do it because you're doing the remote lab on the molar mass of an ideal gas, and I think that it's maybe gonna the calculations might be a little bit tougher, and especially because we have to adjust. Well, I don't think they're that bad. I mean, I did an example of a molar mass of an ideal gas, but the fact that experimentally we have to adjust for the vapor pressure of water. So I wanted to find an example where we have to do that. Anyway, that's my intro. So try and do this problem and then come back and see how you did. All right, helium is collected over water at 25 degrees Celsius in 1 atmosphere. What total volume of gas must be collected to obtain 0.586 grams of helium? And then they give us the vapor pressure of water at that point. And I don't know how to solve this one because I haven't done this one before. So I'm going to look at it and just kind of thrash my way through it just like if I was a student. Obviously with a lot more experience since I'm old as dirt, but anyway. So hopefully you can see how to solve this. Well, volume of gas, well, that tells us right away we're in a PV equals nRT problem, right? And looks like we're given pressure and we're given temperature, and the volume is what we need. So volume, I'm going to write that out. Volume equals question mark, just to help my addled old brain to do this. So it looks like then we need to get the number of moles. And they give us the grams. So I see a clue there. Let's go ahead and figure out the number of moles, shall we? We'll do that first. 0.586 grams of helium. And so I have to look at the periodic table. I'm pretty sure it's 4, but I should probably just make sure that it's a round enough number to be 4. So I've got my periodic table here, and let's stick that under there for people on YouTube to see. Yeah, 4.000 or 4.003. So that's good enough, right? So we can just do 4 grams of helium is 1 mole. That'll give us our at least 3 sig figs. And we'll plug that into our calculator then. So 0.586 divided by 4. Oops, I didn't show that. There we go, 0.1465. And that's our moles of helium. All right, so the only thing that makes this one maybe a little trickier then, so that gives us moles, is what is our actual pressure? I got something in there that's... Anyway, what is our actual pressure here? Well, we can't just plug in 1 atmosphere because they say it's collected over water and they give us the water, the vapor pressure. And so we have to adjust for that. Let's do that. The total pressure is 1 atmosphere. That's the atmospheric pressure right now, which is also 760 millimeters of mercury or 760 torr. But what we need, if we're doing an ideal gas calculation, we need the pressure of just the helium, don't we? We need to know just the pressure of the helium if we're going to calculate just grams or moles and volume of helium. So how are we going to get that? Well, they give us the vapor pressure of water and the total pressure, so Dalton's law, is that the total pressure is the sum of all the ideal gas pressures. And so we can do this. Let's go ahead, and since they give us the vapor pressure of water in torr, let's go ahead and solve it that way. So I have 760 torr is the total pressure. We need the pressure of helium, and the vapor pressure at that temperature is 23.8 torr. And so that gives us the pressure of helium. So we're just going to subtract off the pressure of the water. So 760 minus 23.8, and I get 736.2. So that's the only thing that makes this problem different, right? Is that we have to adjust, and so you have to do that adjustment in the remote lab. All right, now let's plug in the values into PV equals nRT. But we've got it, this has to be in atmospheres, right? So let's go ahead and convert that into atmospheres. 760 torr is 1 atmosphere. So we can convert it like that. So I'll take that pressure divided by 760 and find out what fraction of an atmosphere we have. 0.9687. And that's our helium pressure. All right, plugging all this in then into PV equals nRT. 0.9687 atmospheres. And we don't know the volume, that's what it asked for. We got the number of moles up there, 0.1465. And the gas constant is 0.08206 liters times atmospheres per mole Kelvin. And then this is really important, that 25 degrees Celsius, that has to be in Kelvin or it won't cancel with our gas constant. So 25 plus 273, so we have our 298 Kelvin. All right, so let's solve this. All we got to do is multiply this times this times this and divide by the pressure. Okay, so see if I can show this on there on the YouTube as well. 0.11465 times 0.08206 times 298 divided by the answer that we had in there for the pressure. And I get 3.6, well, actually that rounds to 3.70, doesn't it? Okay, volume is 3.70 liters. All right, hopefully that one will help with the lab, adjusting for the vapor pressure of water. All right, thanks everyone.